Okay, good morning, everyone. It's my great pleasure to introduce Professor Oxley. Professor Oxley right now is a professor of mathematics in the Department of Mathematics and Statistics at the Air Force Institute of Technology. Professor Oxley is also NC State alumni.
Yes.
And he got his PhD in the Department of Statistics here. I think at that time the Centennial campus was not built yet, right?
The what? No, that's
campus.
that's right.
So yeah, it's our great pleasure to have Professor Oxley come back to give us a talk. And I think today Professor Oxley will talk about something very important for many applications. Okay, so without further introduction, so let's welcome Professor Oxley.
Thank you. Well, thank you for the invitation, and thank you for the students that showed up knowing I actually am a mathematician, but that's okay. I think I'm working on an applied problem and it would have your interest. So I want to point out that the Air Force Institute of Technology is actually a graduate school for the Air Force. So we have electrical engineers and physics, math, statistics, aero, operation research, and systems engineering. So I get to be on PhD committees and EE and all that. So I have an appreciation of engineers. So I know that engineering is just as difficult as mathematics. So anyway, all right. So if I remember right, I just press down button. Yeah. By the way, I point out this statement here. I don't represent the government, but they pay me anyway, so I guess. So my outline, I'm going to try to do this. One of the things you learn in the Air Force is how to supposed to give talks. You know, you're supposed to tell them what you're going to tell them, and then tell them, and then you're supposed to tell them what you just told them. I think I'm just going to do the first two. This is what I'm going to try to tell you, then I'll tell you. So to start out with some introduction. So what's the motivation for this research? So the Air Force has a lot of legacy systems, detection systems. Not only does the Air Force have detection systems, but you're seeing detectors all around cities and things like that. So improving the detections of those detection systems is one of the things we want to do. But since I work for the Air Force, I'm focused on Air Force problems. And so we have a lot of legacy detection systems. So, okay, some improvements have come, so we should try to make that detector better. So what are the things we can do to make the detection system better? Well, we could upgrade the sensor. Maybe the sensor has more pixels or whatever the sensor is. We could go in and change the algorithm because maybe there's a better algorithm. Maybe we can insert another sensor alongside with the original sensor. So now we've got two sensors. Maybe the second sensor is a little bit different. Maybe it has a different modality. Or maybe we can just insert a whole new component along with original components. Maybe that would get better performance. So that's one of the things we can do with legacy systems. Or maybe we'll just scrap it and start all over with a whole new design. Or maybe we can just take the legacy system as it is and take a new design and then combine them. So there's a bunch of options here. Okay, so, but making these changes to existing systems and not knowing if I combine something or pull out an algorithm and stick in a new algorithm I think is better, that's going to be, it'd be nice to know what the end result is. Doing all that actually costs a lot of time and money. If you want to put a new sensor on an aircraft, you have to, and then fly it, you got to make it, test it, you got to do all these things. You got to design it, especially if you're going to combine it with another one. And there may be a bunch of different ways that you can combine it. you got to build this new combined system. You got to test it. You got to maybe take it out to Edwards Air Force Base, put it on a aircraft, fly it, test it. That's going to be very expensive. Plus you got to wait in line to get some test pilot in an aircraft to fly it on, and it's going to be very expensive. And then you got to perform a verification, validation on the system. Maybe you do that before you even test it, but you get test data now, you're going to try to verify it. And then you got to determine the performance of the new combined system. Be nice to know if you're going to combine this, if it's going to be any better than the initial and better than the initial ones you got. So if I knew that it wasn't going to be that much better, I wouldn't do all this. Okay. But if I knew, hey, after doing this, I got an idea that, hey, this is going to be much better than what we've got, then we would go through all that time and cost and all that, because we have an idea that's going to be better. Okay? So one of the terms, this relates to how do you quantify the performance? Well, we'd hope that we would have very small false positives and very small false negatives. And so one of the things we would like to do then, instead of doing the false positive, we would like to maximize the true positives while we minimize the false positives. Or maybe there's some other optimality criteria you would like to use. Lightweight, well, that would be important, but that really doesn't tell you that the detection system is better. Maybe it's cheap, so that doesn't really tell you if it's going to be performance is better, but that still is a criteria. So what's my big idea here? If you have a system, you would probably have the Roc Curve, or at least an approximation. Actually, no one has the Roc Curve of a system, because the Roc Curve assumes that you have all the information and everything is running smoothly, stuff like that. So really, you need what a Roc Curve is. Okay, a Roc Curve is a receiver operating characteristic curve. So, hey, let me use this pen here. See if I can write on it.
BD versus BF.
The what?
BD versus
Yes. Yes. So this is the false positive. Here's the true positive. And as you change parameters, suppose a parameter comes out here, then you can get some curve here. This is 1. Since a true positive is a probability, false positive goes to 0 to 1. 0 to 1. Oops. So this would be a curve if you looked at every possible parameter. And right now it looks like it's just one-dimensional. But in a few minutes we're going to talk about higher dimensional versions of that. And so this would give me an idea of how good the system performs as you change parameters. This would be the point right here. I like to get to this because this corresponds to 0 false positives. The false positive is, I think it's, I think that that's an enemy plane, but so I'm going to shoot it down. Turns out, no, it's one of ours. We just shot down our own self. This could be fratricide. Okay, if you're looking for, I consulted with a company that was working on mammography, and so they were looking at breast cancer. So a false positive would be telling the woman, we think you've got cancer. Okay, so come back in a month, we'll stick you with a needle, take a biopsy, and then it'll hurt. And meanwhile, you're also thinking you got cancer, and we're going to charge you too. Okay, so, but the other version is the false negative, where we say, no, you don't have cancer, and 2 years later she comes back with a breast cancer because you missed that one. Now, which false positive or a false negative are you going to live with? So anyway, that has to do with the receiver operator characteristic or this detection. So that's what this is. This is a curve, so that's why I've underlined the curve. Okay, so we'll collect data and try to produce this receiver operator characteristic curve to find out how good the system is. Okay, so my idea is if you've got a legacy system, okay, you already have the Roc Curve. Maybe you have this other legacy system. If I have that Roc Curve, so somebody has a great idea, let's combine them. Okay, is it going to be any better? So before we do all that, build it and test it and all that money, maybe we could just play with the Roc Curves and figure out if it's going to be any good or not. Okay? So I got to do the math on this. Oops, wait a second. Arrow down. Okay, let's see, is that right? Oop. Yeah, so the idea is to combine these systems. And so the buzzword fusion comes up a lot. So let me give you my definition of fusion. Fusion actually came out of a bunch of electrical engineers and computer scientists back in the mid-'80s, I think. So got a colleague that refers to them as the fusion mafia, so they seem to have control of the definition. My definition is combining objects for better results. Now I got these numbered here. So what are the objects I'm trying to combine are detection systems. So if I combine two detection systems, D will just denote a detection system. Script D will be the collection of them. And so those are the objects I want to combine. See, number 2 is results. So I've got some function that tells me how good this detection system is. And so this is going to be some real number. So I ought to be able to, this function should be able to take any detection system in and tell me if it's good or not. I'll give you an example later. So the row function quantifies the performance, which is the results. How good is it? Number 3 is the better. What do I mean by better? Well, I need the performance functional to tell me what's better. So this can go up. Okay.
The minute you touch it with your finger, it starts misbehaving.
Oh, really?
You either touch it with a pen,
right,
and use just
okay.
those arrows.
So I can move it down?
No. But if you want to move it down, it's better to use just those
okay.
arrows.
Maybe it'll fix when I press the arrow down next.
You may have to put the pen down. It may think your finger is the pen.
Say again?
You may have to put the pen back in the tray. Because it may think you're at the bottom. Yeah.
Yes.
Okay. All right.
Pen.
All right. So if I got one detection system A, another detection system B, and I want to quantify how good A is and how B is, and let's just suppose that a smaller number is better, then this would say that A is better than B. So you got to have a way of quantifying better, however you define better. 4 is combining. So suppose we have some rule of combining 2 detection systems. Okay, and that makes a new detection system C. So is that, I think I hit them all. So combining objects, so this is, how do you combine? You need to have some rule. I think I hit them all. Let's see, go to the next slide maybe. Yeah, so the last one was, well, let me see. Number 4, yeah, it's combined. But So after I combine them, so this is a new system, detection system C. Rho tells me how good it is. Is it better than, what do I mean by better? Well, it's got to be better than A, it's got to be better than B. Remembering that smaller is better, so I want this number to be smaller than any of these two. Notice it's less than and not less than or equal, because if it's equal, if this equals performance of A, then I might as well stick with A. Why make a new one? Okay, so combining systems yield better results than the two individual systems. Okay, and so if I'm going to combine this using this rule, and if this is true, then I would say I have fused A and B, and I would call this rule R a fuser. Okay. All right, so let me go cover some basic components of a detection system. So you got some events of some sort of stimuli that you're going to maybe have some energy related to it, or you're going to have a sensor. So S is a sensor that has energy, is going to illuminate something. But the point is there's some sort of stimuli there, and so E is a set of stimuli. S is a sensor. And D, the output, is the raw sensor data. Why the raw sensor data? Well, because the next slide, I'm going to talk about some processors that actually act on the on the raw data. Because you may choose how you want to filter it. I know a lot of sensors probably have built-in pre-processing. Okay. Which is fine. I don't know if you could pop the hood and stick in a new preprocessor, but I'm just talking at a high level here. This could be a feature extractor. It extracts features, and so scriptf is a set of features. And so P is a function that maps the raw data into a feature. Okay, so once you have features, you have some sort of classifier that wants to, specifically for the detection system, I want the label set to be either target or non-target. You could call it cancer or not cancer, things like that. So L is just a set of labels. C, the boldface C, is a classifier. So I'm a visual kind of person. I got to write these diagrams so I see what's going on. So okay, so when we put them all together, from beginning to end, we're actually trying to come up with a system that approximates truth. Well, we don't have truth, right? I mean, you look outside and is that, what kind of car is that? Or is it a car or not? Is that a person? So we do all these compositions. So we do the sensor first, we compose it with the processor, then we compose it with the classifier, and that's the definition of a detection system. You're going to ask me, oh, I haven't given the application yet. Okay, do I need to talk about the application? These are basic components for any, I believe, any detection system. Okay, so the composition, I'll start just writing D of E. Typically, the classifier has some parameters in it. How many parameters? I had a conversation with you about deep learning and all that. Well, you have a lot of parameters in there. So, so this is a vector. Oops. And theta is just a set of the parameters. So you could actually change the classifier around. And so now the detection system depends upon parameter. So for every choice of the parameter, I actually get a set of detection systems. So I'm going to call this set, instead of calling it set, I'm just going to call it family. So I'm going to use a different font here to denote the family. Okay, so for this, it's a single detection system family. Okay. Similarly, the processor probably has a lot of parameters in it. So I have this could be a vector of parameters. So now I got two parameters here, one on the classifier, one on the processor. So this would make another kind of detection system family. And this is a single family, but it's a little bit different. It's different than the previous one. So D2 is not D. Suppose the sensor, you got control over the parameters and sensors. Depends upon the sensor, I guess, but maybe you could change it around. That could be, I guess, if it's an optics one, maybe you have control over changing the focal point and zooming in and zooming out. Well, then the detection system has all these parameters you could vary. So I get another kind of detection system family. But that's not like the first one. It's not like the second one because there's other parameters. Okay, so my point of doing that is that there's many detection system families associated with trying to look at some environment with some sort of stimulus and the label set, is it a target or non-target? Okay, so I'm going to compress some notation and use DSF to denote the collection or the set of all detection systems that takes this as input and spits out target or non-target or whatever your label set is. Okay? But for the discussion, let me just talk about, okay, so that was just all the different possible ways you could have a detection system with a parameter. I think I'm just going to use one symbol for one system. But this talks about, suppose I have a different classifier. Let's just suppose I change one. Maybe it's the same sensor and processor. Is this a different detection system? Actually, with that parameter there, it's different. Is it a different detection system family? Yes. So here is, I'll just define capital A with this parameter to be a different family. Okay, so here's the original one, and here's the new one. I'm going to take the outputs and do a concatenation. So here's the set, target, non-target, target, non-target. I'm looking for a rule that's going to take those and produce either a target or non-target. Well, for detection systems, you've only got AND rule or the OR rule. So let's see, I need to scroll this up a little. So how do I combine detection systems? I'm just going to combine the outputs. See, the input's the same, so from here all the way over to here will be a new detection system. So with two families, I can make a new family. Okay? Well, actually, this statement is with theta and phi fixed. I got two detection systems. I combine them. I make a new detection system. But as I go through every possible theta and phi, I actually make two families. So here's an operation I can perform on two families to make a new family by ANDing or possibly ORing the two systems. Now the question might be, well, which one's better? So I can make a new detection system. Sorry, I should use that. All right, so that's just a quick background on combining detection systems just by combining the outputs. By the way, while I'm talking about it, I could just cut out the classifiers and take the feature vectors and combine those and then pass it to another classifier, and then I would, so that would have a feature rule, and that would be a new family. I could take the output of the raw data, combine those, and then pass it through some processor and some classifier, and that would be another one. But that has to do with feature fusion and sensor data fusion. But right now I'm just going to, with this big idea, I'm just going to stick with label fusion. Some people will call it decision fusion, but I don't call it decision fusion because that's assuming that the machine's making a decision. Hopefully, especially for a pilot in a dogfight, he's going to make the decision. Also for mammography, you hope that the radiologist is going to make a decision versus the machine say, yeah, we're going to biopsy you. So actually, in medicine, you got to, I think the standing rule is you got to have somebody to sue if something goes wrong, right? So you got to have a person in the loop, okay? I know that sounds kind of bad, but I think it's really true. Okay, so now I want to talk about the receiver operating characteristic function. I mentioned the truth, but we don't have the truth. That's why we're making these systems, right? We're sensor, processor, classifier. We're trying to figure out if this thing really is a target of interest or it's not a target. So we're doing this to come up with the truth mapping. So we don't have the truth mapping, but I can talk about it. So if you gave me, so I'm going to go at the far end now. If you gave me a target, wonder what all the events are, or all the stimuli that actually map to that label target. What are all the events over here that are not targets? So this is the pre-image of targets. It's just all the events that truth maps to a target. So I've just subscripted all the events sub T for targets, all the events N for non-targets. So if we have a probability space, so here's your event set, here's the sigma algebra, and then we choose some probability measure. You could choose any probability measure as long as it's defined on that sigma algebra. So from that, then we can talk about the probability of true positive for this detection system for fixed theta. It's a conditional probability, and just writing it out. And then we can talk about the probability of false positive for this detection system for that theta. Very similar for the true positive. Okay, so it seemed like when I first got into reading about Roc curves, everything was one-dimensional. They had a Gaussian, here's another Gaussian, and they just moved theta. Theta was one-dimensional. We're working with high-dimensional systems, and so there's a lot of knobs to turn. So with that, then we actually need to define the Roc function for this detection system family. So if you give me a P between 0 and 1, which corresponds to a false positive, I'm going to go through all the thetas such that the false positive of that detection system is less than P. I want to maximize the true positives. Okay, let me go to picture here. So what I mean is if you gave me if you said 0.3, okay, what are all the true positives? Well, which one would you take? Well, you take the one that's up here on the frontier. Okay, give me any other P down here. Well, you're going to take the frontier. So that's why I'm mentioned the Pareto front. The Pareto front is the top of the blob. Okay, so, and this is in the spirit of Neiman-Pearson. Okay, so if you gave me a detection system family, this could make the Roc function. I'm using Roc function synonymous? Similar?
Synonymously.
Okay, yeah, did you get that? Because he said it right. I didn't. To the Roc curve. Because, let's see. Which way? Where'd it go? There's a blob, okay? There's no function there. Where's the function? You got to pick out the frontier, okay? So I need this maximization subject to this constraint to define the function. So the graph of the function is a curve. Okay, so this just states that if you gave me a detection system, there's actually gave me a detection system, there really is a transformation that makes the Roc function. So, and if I called RCF this collection of Roc functions and DSF is the detection system families, then I actually have a mapping that takes a detection system family and spits out the Roc function. This is just math speak that corresponds to this. Okay. So what are some rules? Okay, so back to my big idea. I want to combine Roc. I got two systems, A and B, and I want to AND them. So I got to build it and all that and test it. But what are the Roc curves? Can I combine the Roc functions for A and B? So if you gave me the Roc function for A, give me the Roc function for B, can you tell me what the Roc function for A and with B is? Well, I get pretty close. So here's the theorem that was done, I don't know, a decade ago. If you had two detection systems family, and you're looking, and these systems are looking for the same thing. Okay, and these systems are statistically independent. Now that's going to be hard to swallow. But let's suppose I live in this magical world where maybe everything holds true, but suppose it is. This formula pops up. So it's the product of the Roc function for A times Roc function for B, but P and Q are different. And notice that the parameters go away. So I don't need to know the internal workings of the system. I just need to know individual Roc functions, and this would give you the Roc function ANDed. Similarly, there's a one for the OR. Again, we're assuming independence. Okay, so again, we don't know if they're dependent or not, but this could give us maybe an idea if it's going to be better or not. Okay, so let me give an example here. Suppose I have 3 systems. I was going to do 2, but there's only 2 curves, okay? Let's make it really interesting. Suppose I got 3 systems. I'm just going to make one up. So p to the 4th, hyperbolic tangent. This will be blue. Here's some other ones that we made up. And let's plot them. Oops. Wait, what happened to the plot? There's the plot. I chose these because the red one crosses the blue one, so it's kind of hard to figure out, well, which one's better. Well, again, you have to choose the performance, then you can, and then you can talk about which one's better. What about the green one? The green one's below, but here it's better than the other 2, but then, again, so you got 3 of them, they all cross. So if one dominated the other one, you would say, oh, let's take that one. We know that's going to be better because the true positives are higher. Okay, but let's see, I think it back. If you gave me three systems, I could look at the individual ones and just see how good they are. But I have the Roc functions for each of those. But I'd like to know what happens for A and B. Let's forget C. Well, what about A and C? What about B and C? This is ANDing. What about if I OR them? Okay, so here's 6 systems that I'd be interested in looking at. But what about if I take all 3 of them? Suppose, well, how can you, well, suppose I AND them all. A ANDed with B, ANDed with C. What about if A ANDed with B, ORed with A? Well, that's different. I don't think that's a typo. A ANDed with C. What are all the different combinations with ANDing and ORing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like maybe I left one off, huh? And then there's a majority vote. So majority vote see, looks like, let me draw a Venn diagram. So if you had A, B, and C, let's see, majority vote would be if any two of the three said it's a target, then you'd go with target. So A and B says a target. A and C says it's a target. B and C says it's a target. Okay? So that's just B says it's a target. And the other guy said no. So this is what, from a Venn diagram, what the majority vote looks like if you did it with sets. So here it is for systems. And these. So AN with B, AN with C, BN with C, and then I take the OR. But there's an equivalent, so there's really only one majority vote, but you can write it this way or that way. Okay, so see, how many did I count? 1, 2, 3, 4, 9 plus, what did I say, 11, so there's 20. I'm not sure I got the count right, so that'll be a homework assignment you'll turn into Dr. Krim. I don't know if I got the count right. But let's use the formulas for ANDing B and C, and then that's AND it with A. I can make the Roc functions. I can make the Roc curves, okay? So there they are. It's easy to plot with a student who knows how to code MATLAB. So I can look at this and figure out, well, which one's the best? Well, you can still see the red, which is A, here's blue, and then there's C. But all the other black ones are all the other ones. We highlighted this one because, okay, that one really sticks out, and it's close to this point, which is good because that would be, you like to have true positive to be 1, but then the false positive to be 0. So, yeah, that looks good, but it depends upon your criteria. Okay, so let's see. Wait a second. I think I got it back in order. Let me zoom in. Okay. In particular, let's look down here. If you were interested in, for example, you couldn't live with a false positive past, let's see, I missed it, say 0.05, okay? Then you wouldn't be interested in this. Yeah, it's way up there, but I can't live with a false positive. Notice that what was the majority vote is actually not as good as something else over here. I'm not sure which one it is, but the black actually is higher for a smaller false positive. So even though the majority vote looks like it's better, it comes down to what's your criteria of goodness, of better. So let's see. Go back to this. I think okay. So I talked about better. Let me give you an example of what better might be. Yeah, so which one is better? So base cost is an example that comes up in statistics. Let me put this back. In probability. So let's suppose you're going to quantify the cost of a false positive. It depends upon the application, right? Would it be breast cancer? Okay, it's just a biopsy, okay, but we will know for sure. Pilot in a war fight, a false positive may be really bad because you're shooting your own. That's fratricide. That's not good. So maybe you can choose this number. The cost of a false negative, you can choose those numbers. You could probably normalize them so that they sum up to 1. But we're going to take those and then multiply them by the false positive for the system A, for that fixed theta. Here's the false negative for that system times that. So basically, the cost is you're going to weight it. Also, part of this cost might have to do with, well, what's the prevalence? What's the prior knowledge of, are there enemy planes out there? For cancer, it would be, well, you might change it if, for example, if a woman, her mother and her aunt had breast cancer. So you might change that because you may be predisposed to have cancer. So you might change it for that person, or the scenario for a dogfight. Especially if you got some information that tell you that, hey, there's nobody should be out here. So you may want to, you could change those parameters. So you could change you could actually play with base cost for the detection system. So here I'm going to go through all possible false positives. I'm going to go through all possible parameters, and I want to minimize this because these are errors, right? These are errors. I want to minimize my errors. So is there some theta that would minimize this once you chose these numbers? Okay. And so this would be a number that corresponds to base cost. I want to point out, though, that the false negative is 1 minus the true positive. Okay? So the false positive could be a P, then the true positive is this. The point of going from here to here is that I already have the Roc function. I could stick it into this expression, choose these two numbers so that they sum up to 1, and then minimize over all possible false positives. And that's going to give me the same answer. This I already know. Okay? I don't know the internal workings of what the false positive and the false negative are. Okay, so this can give me the performance for the system A, but really I forgot the Roc function, so I'm going to come up with a functional that acts on the Roc function. Okay, so let's see. That basically gives me a functional that defines on the Roc function. So the relationship between this function and this function are related to this transformation. Okay. So my goal is to try to convey that there's a lot of information in the Roc functions that we could use to determine which rule we should use. And hopefully this might maybe convince you. And I also will remind you that I'm assuming that the systems are independent. Okay, which is not necessarily the case. But we have some other techniques on ways to determine if the systems really are dependent. So I got some work on that if you're interested in hearing about that. So again, the big idea is I got this information. Can I use it to tell me how to combine over here? Because as you can see here, there's 11 or whatever the number was, almost 20 different ways to combine. Which one's the best? If each one took $1 million to test, it would be good to just do it once. Okay, I think that's it. So I know I'm under. Well, okay. I got plenty of time for questions. So, yes.
First of all, thank you for your talk. It was very interesting. I have a question related to the application of your approach. So you made an example with 3 different sensors, but assume that you have a situation when you have something like 100
Yeah.
sensors. It can happen. You can have cheap sensors and you can use many of them and then use the
Right.
information. Then if you really want to do this, you have to go through 2 to the power of 100 different ways of combining them and then choosing the best one, which is not really practical.
Right.
So have you thought about any algorithmic way to search the space of all possible combinations through the rule that you come up with?
No, but that's going to be, so if you got N systems, how many systems will you come up with if you do all possible ands and ors? It actually forms a, well, I got a paper that says it forms a Boolean algebra of Roc functions. Turns out that's not really correct because there's a property that doesn't hold the absorption property doesn't hold. We messed up, which was bad, but in the process I found out that there are some families of detection systems where you could actually reach in and grab one parameter, reach in and grab another parameter within the same family, and then and them or them, and you could get better results. So we did something wrong on the Boolean algebra. So since it doesn't satisfy absorption, I'm not sure what to call that object, that construct. It's some sort of algebraic structure. We're calling it a near algebra.
Can you
So-
look at it from sort of a functional analytic point of view? Where you have, I can imagine having a tree, and you basically have a dynamic program going through the tree, where all your individual rock curves sitting at the bottom of the tree. In other words,
Yeah.
they're leaves of the tree, and as you're climbing up the tree, you find sort of it's kind of like a wavelet packet type, best
Yeah.
spaces type of,
Right.
Of search, where you search from those and you get the best combination of this is what's going through my mind right now.
It's similar to this absorption rule that
Yeah,
But that can be pretty fast though.
yeah.
Yeah,
It's all-
setting it up as a dynamic program can be done pretty fast.
So I think when I gave that Boolean algebra talk, somebody asked me the question about, and I think my response back then was, well, how many detection systems are we going to put on an aircraft? Okay, back then it seemed to be a good answer, but now knowing that the Air Force is putting all these sensors on the aircraft to detect structural damage, okay, well, you got a wing, okay, it's under a lot of stress, and so here's a rivet hole that's maybe starting to come loose, and so having a sensor on there to determine that, but then you got sensors on the other side, so there could be a lot of sensors, but maybe they're not sensing the same thing. I don't think I'd combine them like that. So I'm not dismissing your question when you got 1,000 sensors that are. If we could really show that you get better performance with really cheap sensors, then yeah, we should do that. But how do we do that in the meanwhile? So and actually, how do you do that? Well, we just make carbon copies of them, but we change the parameters a little bit instead of having to come up with a whole new one. Would that make good performance? And yeah, I don't know. I think I could at least get a handle on if it's worth pursuing, if I could figure out how to do all those thousands and thousands of them. I'll show you the formula if you want. If you have a single family and you reach in and grab a theta and a theta prime and now do it, I'm assuming independence between the two parameters, which is probably not good. That's why I mentioned yesterday in our meeting about the copula theory, where you could figure out how things are dependent based upon the copula function. So, yeah.
The other question I had was in terms of robustness. In other words, now, fine. I mean, suppose I resolve this, this search, and I have an optimal system. But of course, these are sensors, so they fail.
Right.
And then ultimately, you don't want the general to come back to you and say, you know that system you designed?
Right.
It turns out it's not very robust at all.
Yeah.
How, if you have, in other words, how would one ensure, or how would one go about, injecting some robustness?
So it sounds like, okay, let's just say we got 50 sensors, okay? And so we know how to combine them. But then you're saying one of the sensors just fails and dies. So it sounds like we should now reconfigure the 49 that we got. Or maybe how we're combining, well, we can't combine this guy, so we got to...
Ideally, what one would like to do is not having to do that and have a
Not having to reconfigure it?
Not having to reconfigure it
Yeah.
in the sense where you will have a degradation, and you want you want to ensure that the degradation is graceful.
Yeah. So that sounds like a criteria that we should impose so that when we choose a rule, it satisfies this graceful degradation
And it's not
property.
obvious to me how you would do that.
I don't know. That's a good. I'll write that down. I've.
It's not obvious. Yeah.
I'll write it
At
down.
least to me,
Okay. Well, that's good. Yeah. So. Even if you only got 5, so.
Yeah, I mean, you can think
So-
of smaller numbers so that you can actually kind of get.
I know the Air Force is working on, related to structural health monitoring of the aircraft, where the wing bolts into the fuselage, and that if it cracks there, that's bad, okay, because the wing could fall off. So they're trying to detect the onset of a crack, okay? And so, but if the sensor fails, then like, hey, I'm good, right? Well, no, the sensor's not sending you anything. So, so how can you determine if your sensor has failed? Is probably another problem. It almost sounds like a sensor system that's devoted to determine if this sensor has failed. So it sounds like sensors on sensors. But that's going to just explode, I guess. But anyway, we need to come up with those kinds of, yeah, that's a good question. So, other questions?
And another question may be related to Hamid's question.
Yes.
So I'm wondering, for example, how to apply your current method for the situation like this. Suppose you have a current set of detection system,
Yeah.
and you already made a decision. For example, I want to add a new component or new
Okay.
detection system. But before I add the choice of the new system, you have many choices, right?
Yeah.
And how do you have any comments, for example, based on the Roc curve of the current set of detection system? Would that be also informative to help you to select, for example, the best choice from for the new system in order to add it, such that once I add this one,
Yeah.
it will potentially give me the big improvement.
Okay, may see if I understand your question. So you got one system, but you got a collection. You want to know which out of this collection, if I can only choose one more.
You want to add one,
One,
but you have many choices for,
Right.
for that new design.
right.
So then, how
So-
can you make a more informative choice based on the Roc curve of the existing
If I know the
system?
Roc curves of all these,
Yeah.
then
Oh, you don't
I guess I could keep trying them, okay, and then use the
Suppose
formula.
you don't know the Roc Curve of the new system because you haven't.
Oh, okay, I
haven't
don't know
run-
it. I don't, okay.
Yeah, you only know the Roc for the old system. Would that?
Wait, of the old system?
Yeah, the current system.
Current system.
The existing.
Existing one. Yeah. So would the Roc Curve or the exploration of the combination of the
Yeah,
old system to help you to select a better
yeah.
few choice
That's,
from the new design.
Well, if I had a system I can grab from, and I know its Roc function, and I combine them, and now I'm going to take data on the combined system and produce its Roc function, do I still want to know the Roc function of the original one? Then it's kind of like, here's the original one. Oops, not you.
There's a brush there. Yeah.
Okay, and I want to take this one, here's the new one. Okay, so I know that one, because I tested it, right? I know that one, but I don't know that one,
Yeah.
okay? So I thought about this problem. Can I invert the AND operation? It's a Boolean thing, okay? So I need to do, I think, like an absorption operation, I think. But how can I invert this is the question. So
You can use the Morgan's theorem.
the more, okay, which is
Negate and then
Take-
you know,
take the negation of the whole thing?
yeah.
Okay, well then that would be,
Then it turns into a union.
what's the eraser?
Yeah. That one.
There it is. Okay, so I'll erase that. Whoa, too much.
Yeah.
Um,
It's very difficult.
And then this is,
That turns into a union. You have to put down that pen.
then this will be the union. I got the
Yeah.
knot. Actually, I know what the knot is of a Roc function. So I can do this. I can do the knot of that and the knot of that, and the knot of that. So I would know this, and I would know this, but I still don't know that. So it would be easier to take the inverse respect to the OR. I think there's an absorption property for that too. But I have, yeah, I thought about that. So, yeah, but I don't have an answer. Sorry. So
To figure it out.
you just find a smart grad student and, well, I need to find a smart grad student to work on it. So anyway, any other questions? Yeah, sorry.
All right.
Okay, so if no
There'll
questions.
be a quiz later, okay?
Yeah,
Just what I talked about.
that's okay. Let's thank our speaker again.
Thank you.